Mr. Mvakate here again. I'm back with more equilibrium constant calculations. But today, before we can continue with our calculations, I want us to discuss something around the mole. Okay, because since we fill our table using the moles, so sometimes on our statements, it is not always the case that you will be given the amount of the substances in mole. Okay, so we'll have to convert them to what? To the moles. Okay, so today I want us to before we can continue, let us discuss the mole. Okay, so there are quite a number of ways in which you can calculate the moles of a substance. Okay, now for an example, we've got we've got 4 ways. Here we've got 4 ways. Now the first one will be this one, the number of moles using the Avogadro's number. So Elena in grade 12 will be familiar to the Avogadro's number that was introduced in grade 10. So okay, the Avogadro's number is actually the number of particles in 1 mole of a substance. Okay, so if we are provided with what? With the number of particles, if we are provided with the number of particles, we can simply get the mole by just dividing the number of particles by the Avogadro's number. Okay, so we can find the Avogadro's number on our question paper, at the back of our question paper on the information sheet. So it is there. That's where you will find the Avogadro's number. Okay, so you just divide the number of particles with the Avogadro's number, then you will have what? You will have the number of moles. Okay, and then the next one is this one, when we have what? We got the volume of a gas. The volume of a gas. Sometimes of course some substances are in a gaseous form, so sometimes we will be provided with the volume that is occupied by a gas. So if we are provided with the volume that is occupied by a gas at STP, here at STP, okay, the molar volume of any gas at STP is 22.4 decimeter cube. Okay, so you just have to use the volume that is occupied by a gas divided by what? Divided by a molar volume, which is 22.4 at STP. Okay, so when the conditions are not at STP, at STP, therefore we cannot use the molar volume of 22.4, but the molar volume of that particular gas at those conditions will be provided to us. Okay, and then we come to this one, the familiar one. Okay, we mostly use this one. Okay, so when we have the mass of a substance, maybe a solid substance or liquid, or it can be a gas. Okay, when we know the mass of that substance, we just have to divide it by a molar mass. So how do we calculate the molar mass? When calculating the molar mass, we use the periodic table. Okay, so we learned this in grade 10 also, calculating the molar mass. Okay, and then when you got the mass, you just divide it by the molar mass of the substance, then we will be able to get what? To get the number of moles. Okay, so sometimes we can be provided with the concentration of a substance, and now we will want to convert that concentration to what? That concentration to the moles. Okay, so if we are provided with the concentration, we will also have to know the volume of a solution. Okay, the volume of a solution will also be provided to us. If we are given the concentration of a solution, we also need to know the volume of the solution. With these two, we just make N to be the subject of the formula. Therefore, this is going to be N is equals to CCV. Okay, so in this case, this volume is different from this volume. This is the volume that is occupied by a gas. Okay, this one is a volume of a solution. It's a volume of a solution. So with concentration, we also need to have the volume of a solution. Therefore, when we've got those two, we'll be able to calculate the number of moles. Okay, so let us continue with our with more equilibrium constant calculations. Let us continue with that. I have prepared a few examples here. a few examples. Now what we have, and more calculations involving what? Involving KC. Okay, so let us check this one. Number one, consider the balanced chemical equation below. Okay, consider the balanced chemical equation below. Okay, good people, before we can continue with this problem, there is something that I want us to discuss for today. Let me just give you an overview of what we are gonna be doing today. Okay, so today I want us, our calculations will be like this. Okay, so we'll be provided with the what, with the initial mole, and we also gonna have the equilibrium mole, and we're also going to have KC. Okay, so I like to break this problem in three parts. Okay, into three parts. So into three cases. This is going to be case 1, this one is going to be case 2, this one is going to be case 3. Okay, so for each of these, now we just have to use our table to check which case is it. So this will make things easier for us to can calculate our KC or calculate the unknown. Okay, so also what I want us to do today is that we'll do a problem whereby we are provided with sufficient information initially. Okay, and then we've got some information at equilibrium, and we are required to calculate what? We are required to calculate KC. They want us to calculate KC. Okay, on case 2, we are not going to have sufficient information initially. Okay, and then we're going to have some information at equilibrium, and we'll be provided with the KC value, and we are asked to calculate the initial amounts that were not provided to us. And on the case 3, on the third case, we'll be provided with the initial amounts of the substances. We don't have what? We don't have amounts at equilibrium, and then we are provided with KC, so we are required to calculate the equilibrium amounts of the substances. Okay, so but for now, the first question that I will be doing, it will be based on case 1, and the one that we did last week, the one that I did last week, it was based on case 1. So after case 1, I'm going to address case 2. After case 2, I'm going to address case 3, and that will be the end of our session. Okay, so I've got what? Case 1. So here, say consider the balanced chemical equation below. Okay, consider the balanced chemical equation below. 12 grams of H2 is a gas, react with 118 grams of O2 in a 1,5 decimeter cube container. At equilibrium, 9 grams of H2 remains. Calculate the value of KC. Okay, so how are we going to approach this question? This is how we're going to do this question. Okay, now we've got the information initially there. Okay, so I'm gonna say this is for initially. Okay, initially I've got what? I've got what to call H2, and number of moles is what? Mass over molar mass. Okay, molar mass. Okay, so I've got what? I've got H2 there, and I've also have O2 there. So I want the number of moles initially. Okay, so initially the what to call the molar mass of the molar mass of H2, will have to use the periodic table to find the molar mass of H2. It's 1. It's there. It's 1. Okay, so we are going to have N is equals to the mass of H2 is 12 grams. This is going to be 12 over 2 into 1. Okay, so this is going to be 6 moles. 6 mole. Okay, 6 mole initially for what? For H2. Okay, we are not provided with the amounts in moles, but they are in mass. Okay, so we have to convert that mass to what? To convert that mass to moles. Okay, now we have O2. O2, the amount of O2 is what? This is going to N is equals to 118 over 2 into oxygen. The molar mass of oxygen 16. Okay, this is going to be 16. Okay, so what are we going to have? We're going to have 118 divided by 2 times 16. Now we've got what? We've got 3,687. 3,687. Okay, good. Moles. Okay, so these are the initial amount of what? This will be the initial amount initially, okay, of H2 and O2. Okay, now let us go back to our statement. At equilibrium, 9 grams of H2 remains. Okay, so now we have to do for equilibrium. At equilibrium, okay, we are still on that H2. Number of moles is mass over molar mass. N in this case is going to be equals to 9 over 2 into 1. This is going to be 4,5 mole. Okay, good. So by the look of things, with the information that we have here, it seems like we are dealing with case 1. This is case 1 because we've got sufficient information initially and some information at equilibrium, and we are asked to calculate what? To calculate the value of Kc. Kc is the equilibrium constant. Okay, so how are we going to do that? Okay, so when answering the question, we are going to draw a table like this one, and I'm gonna say this is a rise E. This is the ratio initial mole. Okay, so this is the change. On change we have used or formed, which is also in mole. Okay, now we have equilibrium mole, and then we're gonna have equilibrium concentration. Okay, C equals to N over V. So the unit here is mole per decimeter cube. Okay, good. Now draw it like this. Okay, so the reaction is what? It's 2H2, which is a gas, plus O2 gas, to give us 2H2O. Okay, to give us 2H2O. So the ratio here is going to be 2:1:2. Okay, so from the statement we are told that it is hydrogen and oxygen that is in the container. Okay, so we're using moles here, we don't use mass, so we just converted those masses into moles here. So H2 is going to be 6. Initially we've got 6 moles of H2, and we've got 3,687 moles of O2. Okay, so now this is going to, here we're going to put a minus. So why do we put a minus here? Because these two substances are the reactants. Okay, this one is a product, it is formed. Okay, these ones are being used. Okay, these one are being used, and then this one is formed, hence it is positive. So at equilibrium we've got 4,5 moles of what? Of H2. Here is going to be 4,5. Okay, 4,5 mole. So for us to calculate Kc, we need to fill up this table. Okay, we need to fill up this table. Here I said one should write use ratio, so that you know this is the part where you use ratio, because in most cases with my experience, learners tend to confuse this what you call this row and with this one for equilibrium mole. You find learners using now the ratios to fill up these empty spaces here. Okay, so this is that will be incorrect. So you have to use this ratio here for change, used, or formed. Okay, so we need one value so that we can use our ratio to find the others that are not known to us. But because we've got two values in this column, we've got two values, we can be able to find this one. So we started with what? We started with 6. Okay, and at equilibrium we have 4,5. So how much was used here? We can get that by just saying 6 minus 4,5, and then we get what? We get 1,5. What was used is 1,5 mole. Okay, now that we've got a value there, now in order for us to get these two, we are going to use what? We are going to use a ratio. We are going to use the ratios. Okay, so how are we going to use our ratios? We are going to use our ratios in the following way. Okay, in the following way, we are going to say here we've got what? We've got 2. This is going to be 2. Okay, 2. This is 2 is to 2 is to 1. Okay, so we're gonna say 2 over, what do we have there? Because I said you must also use ratio here. We have 1,5 is equals to what we are looking for here, 1 over x. So we do the maths, cross multiplication. This is going to be 2x is equal to 1,5. Okay, so we are looking for x, not 2x. So we divide both sides by 2. So this cancels that. X is going to be equals to 0,75. So we're going to have 0,75. Sorry for that. 0,75. Okay, so now because these ratios are the same, 2 is to 2, so we're going to get the same thing as that here. So this is going to be also going to be 1,5. This is also going to be 1,5. Or if you want to check it, you can check it by doing the same ratio that we used here. So the ratio there is what? Is 2 is to 2. Okay, it's going to be 2 over 0,7. 1, okay, let me just scratch it out. Is 2 is to 2 is 2 over 1,5 is equal to, we're looking for this here. So we have that ratio 2 over x. Cross multiplication, 2x is equals to 2 is to 2. 2 over this. Okay, and then we're looking for that. It's x, cross multiplication, 2x, 1,5 times 2 is 3. We're looking for x, we divide by 2, this cancels that. X is equals to 1,5. Hence we've got that 1,5 there. Okay, so I must have left something earlier here. Here. So the value here is 0. It's 0 because from this question we are told that initially 12 grams of H2 and O2 react with 118 grams of O2 in this container. So we know that initially what is in the container is H2 and O2. So we don't have the product H2O in the container initially. So hence the value here is gonna be 0. Okay, so now we come to find the equilibrium mole. Okay, because this one is a reactant, we go to say what we have initially is going to subtract this. It's going to be 3,687 minus 0,75. Now what do we have? We've got 2,937. Okay, we see 0 plus 1,5. This is going to be 1,5. Now we have the amounts at equilibrium, but for Kc we are not using moles. We are using what? Concentration. Okay, so we have to convert these moles to concentration using this formula. C equals to N over V. Okay, so now where is the volume? We are told that they react in a 1,5 decimeter cube container. Okay, so the volume is 1,5. Now this is going to be 4,5 divided by 1,5. Okay, 4,5 divided by 1,5. Then we're going to have this in mole per decimeter cube. We're also going to have 2,937 divided by what? Divided by 1,5. Okay, we're also going to have 1,5 divided by what? Divided by 1,5. Okay, this is going to be 1. Okay, now we know the concentration there is 1. And then we come to this part. 2,937 divided by 1,5. 1,958. And then we've got 4,5. 4,5 divided by 1,5. This gives us 3. Okay, so we are asked to calculate the Kc. So now we start with what? We start with our Kc expression. So this is going to be Kc is equals to the concentration, because this is a gas, the concentration of H2O squared over H2 squared, concentration of O2. Okay, all these are gases. It's only solid and liquid, pure liquids, that we do not put in our Kc expression. Okay, they are excluded. Solids and liquids, the aqueous solutions and the gases are included in the Kc expression. Okay, so when we substitute, we use curved brackets. Okay, this is going to be squared, and then I'm going to have for H2 here, and I'm going to have for O2 here. What do I have for H2O there? I've got 1 squared. What do I have for H2O? I've got 3 at equilibrium. And what do I have for O2? It's 1 comma, this has to be squared, H2O squared. Okay, squared. Gonna be 1,958. So our value for Kc is going to be equal to 1 squared, 3 squared times 1,958. So the value for Kc is going to be 0,0557. Okay, this is going to be our value for Kc. Now we've got the equilibrium constant. Okay, so now the problem that I covered right now, it was for case 1. Okay, it was for case 1. So I want us to move to case 2, where we will be where for case 2 what we're gonna be doing is we will be provided with what? We will be provided with the amount at equilibrium and also be provided with the value for Kc, and will be asked to calculate the initial amount. Okay. Now let us move to case 2. Okay. So for case 2, we've got what? The reaction below represents the catalyzed step in the contact process. So it's sulfur dioxide reacts with O2 to give us sulfur trioxide. Okay, so this is the balanced chemical equation. So initially we've got 4 moles of sulfur dioxide and an unknown moles X of O2 are sealed in a 2 decimeter cube flask and allowed to reach equilibrium at a certain temperature. At equilibrium, it is found that the concentration of SO3 present in the flask is 1,5 mole per decimeter cube. Calculate the number of moles of O2 gas initially present in the flask if the equilibrium constant is 4,5. Okay, so we do not have it's not known. The amount of O2 gas initially there is not known. Okay. And then we are given the amount at equilibrium in what? In mole per decimeter cube. This is concentration. So we have to convert this concentration into moles. So how do we approach that this question? This is how we're going to approach this question. Okay. Now we first start with the table. We first start with the table. Now, we first start with the table. Okay. Now, okay, we have our question there. Now, with the table, we're going to have what? We are going to have rise E. So this is going to be the ratio initial mole which and change which is used or formed. This is also mole. Okay. Equilibrium mole and also equilibrium concentration is equals to N over V in mole per decimeter cube. Okay. Mole per decimeter cube. Okay, so now it's 2SO2 that reacts with O2 gas. This is also a gas to give us what? To give us 2SO3 gas. So this is 2:1 2. So initially we've got 4 moles of SO2, 4 initially, and unknown, okay, X moles. Okay, they are sealed. So these two amounts are the ones that are sealed in a 2 decimeter flask. So we don't have SO3 sealed in the 2 decimeter cube flask. So this one is going to be 0. We are going to have 0 there. So because these two are the reactants, we're going to have negative, negative, and this one is formed. This one is going to be positive. Now what do we have at equilibrium? What do we have at equilibrium? At equilibrium, it's found that the concentration of SO3 present in the flask is 1,5. What? The concentration, this concentration is what? It's 1,5. The concentration at equilibrium. Okay, So we need to find the number of moles of SO3 at equilibrium. Okay, and because we've got the volume is 2, the volume there is 2, the volume the volume is equals to 2 decimeter cube, and we know the concentration is 1,5. Now we can find what? We can find N. We can find N. So how can we find N? We're gonna say N is equals to CV, and then N equals to CV. This is going to be 2. No. Okay, I just swapped the values. 1,5. Okay, but this one is for volume, this one is for concentration. So this is going to be equal to 3. We're going to have 3 mole. So here we're gonna have 3. Okay, at the beginning of this lesson I did mention that sometimes, well, it's not always the case that we are going to be having the values in what? In moles. Okay, sometimes it will give us concentration and volume. We'll have to find the number of moles, and we use N equals to CV. So this is the case. Now in the previous question we were provided with masses of substances, and we had to use the molar mass to find the number of moles. Okay, now we have to fill up this table. Here I said we must write what? We must write use ratio, so that we always know this is the part that we use what? This is the part where we use the ratio. Now here is 0 plus to give us what? To give us x. So this is going to be 3 here. We're going to have 3 here. Okay, because we started with nothing, and we have 3 at what we call at equilibrium. So it means what was formed is 3. What was formed is 3. Okay, so now we use the ratios. Okay, because these two ratios are similar, are the same. 2 is to 2. It means what we have there is going to be the same as that. So we're going to have 3 there. Okay, so now we are looking for what? Now we are looking for this one. This one is not known to us, but we know the ratios, and we know what we've got a value there. Now we can find that using what? Using the ratio. So for O2, we're just gonna say 1 over let's just call this K. Let's just call it K, so that we don't use X, just to avoid confusion. This is going to be equals to 2 over 3. We've got 3 there. Okay, so cross multiply, this one is going to be 2K is equals to 3. We are looking for K. We divide by 2, divide by 2, this cancels that. K is equals to 1,5. So we are going to have 1,5 here. 1,5 here. 1,5. Okay, so now how do we get to equilibrium? We just say 4 minus 3. 4 minus 3 is 1. How do we get here? X minus 1,5, x minus 1,5. Okay, and then we have to get what? The equilibrium concentration, because for Kc, for us to use the values, or to substitute on our Kc expression, we need to have concentrations of these substances at equilibrium. So the concentration, equilibrium concentration. So the volume here, we are told that the volume is 2. Okay, so we got equilibrium mole. So how do we get concentration? We use this formula here. So this is going to be equals to 1 over the volume is what? It's 2. So here we're going to have x minus 1,5. Okay, so divide by what? Divide by 2. Here we already have the concentration. Okay, so this is going to be 0,5, and here this is going to be like this. It remains, you leave it like that. Okay, now we come to our Kc. Okay, come to our Kc. Now Kc is going to be equal to SO3 SO3 what? Squared over SO2 what? Squared, and the concentration of O2. Okay, now we are provided with the value of Kc. What to call? Calculate the moles of O2 gas initially present in the flask if the equilibrium constant Kc at this temperature is 4,5. So we come here, we substitute 4,5. What do we have there for SO3? We have 1,5 squared over SO2. SO2 is what? Is 0,5 squared. Okay, now what do we have for O2? For O2 we have x minus 1,5 divided by 2. Okay, so we just do the maths. And then when we do the maths, we just take this one here and we take this one there. Okay, this is more like cross multiplication. Now we are going to have x minus 1,5 divided by 2 is equal to, what is that? 1,5 squared over 0,5 squared multiplied by 4,5. Okay, so I'm just going to punch everything here in the calculator. I'm going to have 1,5 squared, 0,5 squared, and 4,5. 4,5. Okay, so I'm getting 2. The answer is 2. So now I'm going to continue with these calculations on the side. Okay, so we are going to have x minus 1,5 over 2 is equal to 2. Okay, so when I punch this on the calculator, what do I get? I get 2. I get 2 there. It's 2. Now cross multiplication, x minus 1,5, I'm getting 1. 2 times 2 is 4. We transpose this one, x is equals to 4 plus 1,5. So x is going to be equals to 5,5 mole. Okay, so the number of moles of oxygen initially is going to be 5,5 mole. So this is how you do case 2. Okay, please take some time. I'm just going to give you a minute just to go through this question. If you are somewhere in the world, you can just take some time to copy my work. Okay, so presenting here to those who just joined us is Mr. Mvakade Kamva. Okay, our organization that is providing you with these free lessons, it is Kagiso and Kamva Math and Science Consultancy. Okay, good people, I'm back. Now we are going to be discussing case 3 of the problems that we can expect to get when calculating KC. Okay, so right now we just discussed case 2 where you will be asked to calculate the initial amount or initial moles of a substance, okay, and you will be provided with the equilibrium amount, some information about the equilibrium amount, and you will also be provided with the KC. So now what we are going to be doing next is case 3, where we will be provided with the initial mole and we do not have anything for the equilibrium, and then we will be also be provided with the equilibrium constant. Okay. So Learners, this question number 3, you can do this question. This question is similar to the one that we just did. Okay, so you can just pause this question, this video after we are done with this presentation, and then you can come to this part, and then you pause to this part, and you try to solve those x moles of H2. Okay, so if you are getting problems, you can always rewind the video and go check how I managed to do the previous problem, the number 2 problem. Okay, so now number 4, with this one we are going to cover case 3. Study the balanced chemical equation below. Okay, now what do we have? N2 gas react with O2 gas to give us nitrogen oxide. This equation is balanced. It's 2 here and 2 there. It's balanced. So initially 2 mole of nitrogen and 2 mole of oxygen are mixed in a 5 decimeter cube sealed container. So the equilibrium constant Kc for the reaction at this temperature is 1,2 times 10 to the power negative 4. Calculate the equilibrium concentration of NO gas at this temperature. Okay, like I said, good people, we don't have what we are provided with sufficient information initially, and we are also provided with Kc. So we are asked to calculate the equilibrium amount of NO, nitrogen oxide. Okay, so how are we going to do that? So we are going to be doing that in the following way. This is how we are going to approach this question. Now we've got, okay, let me just fold this one. Good. Now we have to use what? We are going to be using a table, okay, like we've been doing with the previous questions. We have to make a table and fill up the table, and then we go to Kc because we are provided with Kc, and we calculate the unknowns. Now what we can do now is that we are going to start with the table. Rise E. This one is the ratio initial mole change used or formed. Equilibrium mole and equilibrium concentration C equals to N over V equals to N over V. The units are mole per decimeter cube. Okay, we draw a table like this one. Okay, so we've got N2O2 reacting to give 2NO, so it's N2 plus O2 to give us 2NO. Okay, so it's 1 1 2, the ratio. So initially we are told that we've got 2 mole of nitrogen and 2 mole of oxygen mixed in a 5 decimeter cube sealed container. We only have N2 and O2 initially, because from this statement that's what we are being told, or what you can take out from that statement is 2 mole of that and 2 mole of this. Okay, and then we've got what? We've got 0. We've got 0 for NO. Here it's going to be 0. Here we write negative, negative. This one is positive. And we write what here? Use ratio. Okay, write use ratio. And that is it. From what we have, we are also given what? Kc, only Kc. So we are told that, what to call? Kc. Now we have to start with the expression for Kc. Kc is what? Kc is, because these are gases, they are all gases. So it's gonna be NO squared over N2 and O2. So we are provided with the value for Kc. So how are we going to fill up this table? Okay, so this is how we're gonna do it. Okay, we're gonna say X amount from the ratio. Okay, it's 1. Okay, X amount of N2 will react with X amount of what? Of O2 to give us 2X amount of what? Of NO. Okay, so X moles, we have X moles that react of N2 that react with X moles of O2 to get what? To get what to call 2X moles of NO. Okay, good. So we continue like that. After doing this here, we continue like that. We're gonna say 2 minus X for us to get the equilibrium mole, and we also get 2 minus X. Here I'm going to get 0 plus 2X is gonna be 2X. Okay, so for equilibrium concentration, we are told that the volume of the container is 5 decimeter cube. Okay, it's 5 decimeter cube. Now this is going to be 2 minus X divided by 5. This is the equilibrium concentration. 2 minus X divided by 5. And also here this is going to be 2X over 5. Okay, so I come to my Kc, since I have the concentrations at equilibrium. So the Kc here, we are told that the equilibrium constant for the reaction at this temperature is 1,2 times 10 to the power negative 4. So we're gonna say 1,2 times 10 to the power negative 4 is equal to 2x over 5 squared over 2 minus x over 5 and 2 minus x over 5. Okay, good. Now doing mathematics, we know that when these things are the same, when we multiply them, we can just multiply the 2 and we're gonna have a square. Now we can say 1,2 times 10 to the power negative 4 is equal to 2x over 5 squared over 2 minus x over 5, also squared. Okay, so when multiply the 2, we're going to have 2 minus x over 5 squared. Okay, so now doing the math, I'm going to introduce a square root on both sides. I'm going to have 1 comma 2 times 10 to the power negative 4 and 2x over 5 squared over 2 minus x over 5 squared. Okay, so I introduce a square root there, I introduce a square root there. Okay, so this square root here will apply for this top part and it also apply for the bottom part. Okay, so what am I going to get? I'm going to get what is it, 1 comma 2 times 10 to the power times 10 to the power negative 4, 1 over 2. I'm going to get 0 comma 0 1095. Okay, so on the top part this cancels that and this cancels that, so I'm going to have 2x over 5 over 2 minus x over 5. Okay, so doing the math, if we want to change this operation sign to a multiplication, so this denominator will become the numerator and this numerator will become the denominator. Okay, so we're going to have 0 comma 0 1095 which is equal to 2x over 5, the top part. Now we change the operation sign, to 5 over 2 minus x. Okay, so this 5 cancels that, now we are left with 0 comma 01095 is equal to 2x over 2 minus x. Okay, so I'm going to finish this calculation on this side. Now cross multiplication, going to have 0 comma 01095 times 2 minus x is equals to 2x. Now this is going to be times 2, 0 comma 0219, okay, this one, okay, minus 0 comma 01095 x is equal to 2x. Okay, is equal to 2x. Okay, so we transpose this one to the other side. Now we're going to be left with 0 comma 0219 which is equals to 2x plus that 0 comma 01095 x. So we add the 2 plus 2, we're gonna get 0 comma 0219 is equal to 2 comma 01095 x. Okay, so we divide both sides by this because we're looking for that x. So we divide both sides by 2 comma 01095, 2 comma 01095. So this cancels that. X is going to be equal to 0 comma 0219 divided by answer. This is going to be 0 comma 011. Okay, 11 what more. Okay, but still with this x with this X, which is equal to 0,011 mole. We haven't answered the question yet, because the answer, we're asked to calculate the equilibrium concentration of NO, the equilibrium concentration of NO. So the equilibrium concentration of NO is 2x over 5. Okay, so in order for us to get the concentration of this NO, we have to take this X that we just solved here, we substitute it there, and then we punch that in a calculator, and we get the concentration of NO. Okay, so let us do that on the next page, on our next page. Okay, now the concentration of what? Of NO, where at equilibrium is equals to what? Is equals to 2x over 5. So this is going to be 2 over 0, 0,011. Okay, over what? Over 5. This is going to give us 2 times the answer divided by 5. Okay, this is going to give us 4,36 mole per decimeter cube, because now this is what? This is the concentration. This is the concentration of what? This is the concentration of NO. Okay, there, this one, NO at equilibrium. So the concentration in terms of X, now that we've got X, we have to substitute it there. Okay, so if they ask for equilibrium mole, we'll take this X and substitute it there. Now we'll get what? The equilibrium mole of this. Okay, so that is it for me for today.